When an ultra-fast laser pulse strikes a glass surface, standard optical metrics fall apart. At these intense peak powers, the linear equations we use to predict light transmission simply fail to describe how the material will actually behave. To understand what happens inside optics driven by high-power regenerative amplifiers, optical engineers have to measure a different parameter, the material's third-order nonlinear susceptibility. This complex susceptibility manifests physically in two distinct measurable ways. We divide it into nonlinear absorption and nonlinear refraction. Nonlinear absorption is an intensity-dependent drop in the total amount of light transmitted through the optic. This is driven primarily by multi-photon absorption processes that only trigger at extreme energy densities. Nonlinear refraction is an intensity-dependent change in the material's actual refractive index. In the laser industry, you will commonly hear this referred to as Kerr lensing. If an engineer puts a standard optic into a high-power beamline without accurately quantifying both of these specific parameters, the beam can violently distort, or the optic itself can shatter. The definitive laboratory technique to isolate and measure these two properties is the Z-scan, originally developed by Eric van Strijland. The method relies on a single precise mechanical action, translating a material sample along the z-axis of a laser beam to map spatial phase distortions directly into measurable changes in light intensity. The process begins with a tightly focused Gaussian beam. The beam waist, the narrowest point of focus, provides a mathematically predictable, highly localized gradient of irradiance. By physically sliding a thin optical sample along the beam path and directly through this waist, the material is forced to experience a continuous curve of known peak intensities. From the resulting photometric data, engineers extract the material's exact two-photon absorption coefficient, denoted as beta, and its nonlinear index of refraction, known as N2. A simple one-dimensional mechanical translation converts a single laser pass into a complete profile of complex third-order nonlinearities. On the optical bench, the setup begins with a pulsed laser source, a Spitfire XP regenerative amplifier, firing a beam through a long focal length lens. For the mathematics of the Z-scan to hold, the optical sample must be geometrically thin. Specifically, its length must be shorter than the focused beam's Rayleigh range. A motorized translation stage grips this thin sample and pushes it precisely along the optical axis, passing straight through the exact focal point, which we designate as z equals 0. After the light passes through the sample and diverges past the focus, it hits a beam splitter, dividing the transmitted pulse into two diagnostic paths. Splitting the post-focus beam allows the system to simultaneously measure two distinct photometric responses from a single physical pass of the sample. Acquiring both data streams concurrently during one continuous movement ensures the absorption and refraction data map to the exact same irradiance levels, eliminating the cross-calibration errors found in separate testing setups. Following the first split beam path takes us to photodiode 1. Here, the detector captures the entirety of the unapertured transmitted light. Because it collects all the light, spatial phase changes or dynamic beam widening do not affect the power reading. Therefore, any drop in the total detected power along this path must be the direct result of multi-photon absorption occurring inside the material. Far from the beam waist, local irradiance is low, and normalized transmittance remains stable at 1.
As the sample translates across z equals 0, irradiance maximizes. Multi-photon absorption spikes, carving a deep, symmetrical dip into the curve. By measuring the exact absolute depth of this minimum transmittance, we can mathematically calculate the material's two-photon absorption coefficient, beta. By intentionally ignoring all spatial beam dynamics, the open aperture setup seamlessly isolates the imaginary part of the material's third-order susceptibility. We now shift to the second detection path. Before the light reaches photodiode 2, an iris is positioned to intentionally clip roughly half of the beam's outer intensity. This simple mechanical aperture acts as a filter, transforming variations in the beam's radius into highly measurable amplitude fluctuations. This brings us to the Kerr effect. At extreme intensities near the focal point, the intense laser light actively modulates the local index of refraction, functionally turning the material into a transient optical lens. If a sample features positive self-focusing and it sits slightly before z equals 0, the induced lens effectively collimates the incident beam. This tighter profile easily slips through the fixed iris, yielding a distinct peak in detected transmitted power. Past z equals 0, the optical geometry flips. The self-focusing lens forces the diverging beam to expand outward, clipping heavily against the iris. Blocked by the iris, the detector registers a severe drop, a sharp valley in transmitted power, before returning to baseline. To extract the nonlinear index, N2, engineers calculate the absolute amplitude difference between this measured peak and valley. The closed aperture setup exploits physical beam clipping, translating pure phase modulation directly into a quantifiable power curve. In the real world, optics driven at high intensities rarely exhibit just one of these effects. Most materials demonstrate nonlinear absorption and nonlinear refraction simultaneously. This graph illustrates a Z-scan where both phenomena are active. This topmost curve is the raw closed aperture measurement. Because the underlying absorption dip drags the total power down, the refractive peak-to-valley shape appears visibly skewed and asymmetric. Because the modern Z-scan apparatus captures the open and closed beam paths concurrently, we have exactly what we need to mathematically decouple the two effects. Engineers take the raw asymmetric closed aperture data and divide it by the symmetric open aperture transmittance, shown here in the middle. The bottom graph displays the result of this division. The arithmetic strips away the absorption artifact entirely, yielding the true, perfectly symmetrical nonlinear refraction curve. Let's apply this method to a specific engineering requirement, selecting optical window materials for a multi-millijoule regenerative amplifier. When 3mm windows face identical focal intensities, the data shows a stark difference. The Z-scan yields an N2 value of 2.9 times 10 to the negative 20 for fused silica, and a much higher 9.7 times 10 to the negative 20 for BK7 glass. The signal confirms BK7's nonlinear refractive index is more than 3 times greater than fused silica, making it highly susceptible to severe Kerr lensing. Furthermore, the open aperture data reveals that BK7 suffers from measurable nonlinear absorption at these peak powers, while fused silica remains virtually transparent. The Z-scan provides the exact empirical measurements needed to make design decisions. It demonstrates exactly why standard materials like BK7 fail under ultra-fast regimes, dictating the necessary use of fused silica or purely reflective optics.